Hello everyone. My paper title is First-order approximate analytical expression of the optical incident electrical waves at an interface of the porous medium saturated with a non-viscous fluid. The contents mainly concludes 5 parts. The first part is exact the approximate analytical equation. The first part contains 4 steps. 1. The displacement vectors of the porous medium caused by the propagation of the fast P wave, S wave, and the slow P waves. And the total displacement vectors of the porous medium can be expressed as following equation. 2. The displacement vector of the pore fluids related with the rock skeleton W and the static pressure of the pore fluids P and the total stress between two porous medium tau can be expressed as this equation. 3. When the fast P wave incident from the upper medium to the interface of the porous medium, 3 kinds of the reflected and the transmitted wave are generated in the upper and the lower medium respectively. Similarly, the upper and the lower layers also have another incident elastic waves. Similar to Aki and the Rachel 1980, 36 kind of reflection and the transmission coefficients at the interface between the two porous medium can form a scattering matrix like this. 4. We introduce the displacement and the stress expression of the upper and the lower layers into the displacement and the stress boundary conditions, and the derived equation of the scattering coefficient like this. Taking full account of the approximation of the relevant parameters in the appendix A, the matrix L, and the matrix N in the above scattering coefficient equation can be further approximated like this. The second part is exact analytical expressions. The second part contains the 3 steps. 1. Substituting inverse matrix expression of the 3-dimensional block matrix in equation A-6 into the above approximation equation. The following equation can be obtained like this. 2. Solving the above equation and fully considering the relationships among the 2-dimensional submatrix and the expressions of the submatrix can be derived as this equation. 3. Solving 2-dimensional submatrix and their composite forms step by step and substituting the result into above equation. The analytical solutions of 36 scattering coefficients are finally derived. Here are 3 sets of expressions. For the detailed solution of the above the 2-dimensional submatrix and its combinations, please see appendix C in paper. The third part is approximate analytical expressions. Approximate analytical expressions. Approximate expressions of elastical and physical parameters of rock selectance and the pore fluids. There is a non-linear relationship between the resolved scattering coefficients and the parameters of rock, pore, and the pore fluids in exact analytical expressions like equation 19 to 27, which is difficult to be applied in the practical production. Under the assumptions of weak elasticity and the small angle incidence at the interface of a porous medium, we first make approximate transformation of the relevant parameters in exact analytical expressions in equation 19 to 27. And with the first and the second order approximations of the relevant parameters in table C-1 and C-2 being substituted into the exact analytical expressions and ignoring the second and higher order terms of the final results. The first order approximate expressions of 36 scattering coefficients can be obtained. The first order approximate expression of scattering coefficients can be described by the fast p wave velocity, s wave velocity, slow p wave velocity, equivalent density, bias parameters, and the displacement amplitude ratio corresponding to the slow p wave. Here are the two sets of expressions. Considering the symmetric in the refraction and the transmission coefficients, the approximate expression of the scattering coefficient can be expressed like this. The fourth part is model test and analysis. For verifying the correctness of the exact analytical expressions and approximate analytical expressions, and analyzing the effect of the pore and the porous fluids on response characteristics of the elastical wave, a sandstone pore medium model is established. The Table 3 and the Table 4 show the parameters of the rock skeleton and the porous fluids required for the model respectively. Substituting the parameters of the lithosity and the pore fluids in the Table 3 and 4 into the analytical equation, exact analytical expressions, and the first-order linear approximations. We verified the correctness of the derived analytical equations and expressions, and analyzed the response characteristics of the various scattered waves. The following is a comparison chart of the p-wave reflection coefficient calculated based on the exact equation and the exact analytical expression, like the left one, and a comparison chart of the fast p-wave reflection coefficient calculated based on the exact equation and the approximate equation, like the right one. The fifth part is conclusions. The conclusion parts include 3 points. First, the priori assumption. The course of the porous medium is much more complex than that of the single-phase medium, and the derivation of the analytical expressions and expressions need to be based on a series of assumptions. 2. Significance. Combined with this research, the inversion of the porous fluids parameters based on the porous medium theory can be realized. Realizing this parameter inversion can further solve the problem of the low identification accuracy of the porous fluids in complex oil and gas reservoirs. 3. Insufficiency. Our research results are derived on the basis of the series assumptions, and there may still be some application limitations for more complex oil and gas reservoirs. This requires following researchers to further consider more complex situations. Thank you for your listening.